The information in this module is accurate and complete to the best of our knowledge. All recommendations are made without guarantee on the part of the author or the sponsoring institutions. The author and the sponsoring institutions disclaim any liability in connection with the use of this information.
A solution to either the global, semi-global, or local sequence alignment problem is an alignment that achieves the maximum score over all possible alignments of the input sequences. Since no deterministic formula returns this maximum, we may attempt to direct a computation of this maximum. This is computing and comparing the scores of all possible alignments. But how many alignments of two sequences are there? This presentation answers this question. Explain the reduction of the problem of counting alignments to the problem of computing combinations. Explain why the number of alignment grows exponentially and the consequences of this result to the computation of global, semi-global, and local alignments. The question here is in how many ways can these two sequences be aligned? Notice that a direct search for an alignment with optimal score must consider all possible alignments. One may guess that there are quite a few alignments, but believe that a computer can produce and score each of them to decide which one is the optimal. This module will show that no computer system will return a solution of the global alignment problem in reasonable time if it's programmed to perform a direct search. Here are a few randomly taken alignments in the set of all possible alignments. These are probably natural choices as they emphasize some similarities between the sequences. These are still some other possible alignments. Some of them are less natural, as they emphasize dissimilarities rather than similarities. Nonetheless, each of them is an alignment between the given sequences, and if we are to consider all possible alignments, these are also in the list. In order to count how many alignments there are, we first paint the rows in the alignment with different colors. Next, we insert a blank cell to the right of each red character and to the left of each black character, and push the second row up to consolidate the alignment in a single row. And finally, we eliminate the gap symbol cells. What we get is a single row representation of the red-black alignment, which we call a red-black intercalation. Since the red-black intercalation consists solely of the letters of the sequence, its length is always the sum of their lengths. This is 6 plus 7 equals 13 in this example. It is worth noticing that the alignment can be retrieved from its red-black intercalated sequence. Indeed, given a red-black intercalated sequence, we insert first the gap between each pair of consecutive characters of the same color. Then we split the sequence in two rows, one formed with odd-numbered entries and the other with the even-numbered ones, as shown in the illustration, and end by eliminating the blank spaces. This retrieves the original red-black alignment. Since we can go back and forth between alignments, the red-black intercalated sequences, there are as many intercalated sequences as global alignments of two given sequences. We don't really need the letters in the sequence, as they are always placed in the same order. For instance, the first black cell is to be occupied by an A, the second by a T, the third C, and so on. All that is needed to identify the associated alignment is the distribution of red and black cells in a red-black array. Each such distribution corresponds to a unique alignment, as illustrated in these two examples. Here is a different choice of red-black cells with its corresponding alignment, which, as expected, is different from the previous one. And here is one of the so-called unnatural alignments. This is to emphasize that each black-red distribution in the array, independent of its nature, does correspond to an alignment. The previous discussion demonstrated our main claim, which is a classical instance of problem reduction. Indeed, we have reduced the problem of counting the number of alignment between two sequences, whose solution was not known. to the problem of counting all possible selections of n cells in an array of n plus n cells, a combination problem that has a very well-known solution. The number of different selections of R elements out K elements, where K is greater than or equal to R. In a selection with order, the same elements taken in different order are considered to be two different choices, while in a selection without order, these choices are the same. For example, if one wants to know how many choices of 4-digit ID card number can be made, certainly the order of choice is important. For example, 3523 and 5323 are different ID numbers. But if one wants to select a committee of 4 members, different orders of choice of the same people does not change the resulting committee. The formula for counting the number of potential choices of R elements in a set of K, with and without order, are called combination formulas. As it can be seen, these formulas involve factorials, which usually translate into very large numbers. For example, the number of 4-digit ID numbers, which must be computed with the formula for combinations with order, is 5040. On the other hand, the number of possible 4-member committees is to be computed with the formula for combination without order is 210. This is a number of alignments between the sequences that we have used for illustration, a surprisingly large number for a rather short pair of sequences. Indeed, the number of alignment growth vary rapidly with the length of sequences. Here we use the combination formula to compute the number of possible alignments of a pair of sequences of length n. Does this table show an exponential growth? As a matter of fact, the number of approximations grows exponentially. This is better shown by approximating the number of alignments with a formula derived from an application of the Moivre-Stirling's approximation to factorials. As this table shows, the Moivre-Stirling formula provides a close approximation to the number of alignments. And the shape of the graph confirms the fact that the number of alignment growth exponentially with the length of the sequences. Through red-black intercalations, we have reduced the problem of counting the number of possible pairwise sequence alignments to a simple combination problem. As a result, we know now that the number of possible alignment growth exponentially with the length of the sequences. In particular, this makes unfeasible a trial and error search for an alignment with maximum score.